Okay, welcome back to part 11 of lecture. Now we'll talk about energy levels in isolated atoms, all right? So I want to make sure I distinguish between this part, which is uh, covering LOs, K, L, and M, and the previous part, where I was covering LOs, the previous two LOs, I and J. Right? This particle in an infinitely deep potential well is very much theoretical. Okay, of course, there are real life things that approximate this thing, but this is a very theoretical idea. 19.6 is very theoretical, and you need to know this formula. Okay, this formula does not apply to 19.7. Okay, just to let you know, this part I'm covering, that formula earlier does not apply to this part. Okay, just to make sure you understand that. Okay, because this one got a different formula. This one is a more realistic case whereby we talk about hydrogen atoms, for example. Okay, so we'll look at Kj and L, K, L, and M, LOs, right? We'll start with this part, atomic structure and discrete energy levels. Atoms are the building blocks of matter, as we know, consist of a nucleus surrounded by atoms. In isolated atoms, these electrons occupy specific energy levels or orbitals characterized by principal quantum numbers n, right? So the number n is actually called principal quantum number, right? So principal quantum number is a positive integer that primarily determines the energy of an electron in an atom. So in this part, we are specifically talking about electrons in an atom. Okay, so this is a quite realistic case. In quantum mechanics, we find that electrons in atoms can only exist at certain allowed energy states, which are quantized, meaning they have discrete values. The lowest energy state is n equal 1, is called the ground state. Any states above these are called excited states. Right? The Bohr model of atom provides the simplest illustration of the discrete energy levels. In this model, electrons can only occupy specific circular orbits around the nucleus. Each corresponds to a particular energy level and principal quantum number. For example, the state n equal 1 represents the lowest energy orbit, while 2, 3, and 4, and so on progressively represents higher energy levels and larger orbits. While more complex atoms have more intricate arrangements involving additional quantum numbers, the principle of discrete energy levels characterized by principal quantum numbers holds true for all elements, right? Generally, you don't have to worry too much about more complex atoms. If they really want to touch this, they'll have to give you a very guided type of question. We normally just deal with hydrogen. Right, so these things you can read yourself. I'm not going to go through. Right, energy transitions and spectral lines. Right, electrons can move between these energy levels by absorbing or emitting energy, right? So this is, for example, the nucleus, right? And the electron can exist in this orbit or this orbit or this orbit, right? So n equal 1, n equal 2, n equal 3. N equal 3 is a higher energy level than n equal 1. For me to go from n equal 1 to n equal 3, I need to absorb energy, right? So for example, if I go from here, n equal 1 to n equal, what is this? 5, right? I need to absorb this amount of energy, right? The spacing here is an indication of how much energy is needed. So this spacing is larger than this spacing. So from n equal 1 to 2, I need more energy than n equal to 2 to 3, all right? So if I jump here, I need more energy than I jump from 2 to 3, all right? That's what this spacing means. However, energies in excited states are unstable and they can only remain at the excited state for a very short period of time, typically in nanoseconds, right? So once they get excited up, in nanoseconds, they'll drop back down, right? They can drop back down in a lot of ways. Later, I'll show you. Okay, immediately when they drop down, almost immediately when they drop down, right? This is called de-excitation, and these energy changes will result in the formation of photons. That means light, right? Because if I drop from here to here, I lose energy. The energy actually produces light particles, or let me rephrase. It's not light particles. It is electromagnetic waves, right? Photons. Okay. So particles of light, just be careful, it's not just visible light, it also includes infrared and ultraviolet and so on and so forth, right? So the energy levels of each photon is equal to the energy difference between the levels involved in transition. Following the equation E equal hf, right? This is from Einstein's suggestion, where h spans constant and f is the frequency of light. So if the gap is bigger, let's say I drop from here to here, the frequency will be higher, as opposed to if I drop from, for example, this point to this point. Right? So larger difference, greater frequency, and therefore greater the energy, right? These energy transitions give rise to spectral lines. Each possible transition between the energy levels produce a photon of specific energy corresponding to a particular frequency or wavelength, right? Emission spectrum and absorption spectrum we'll discuss in the second part, right? So don't worry too much about this for now. Right, now let's look at the uniqueness of these energy levels, right? So this is something you'll be commonly given in the exam, or you may have to draw this yourself, right? Obviously, they won't expect you to memorize all these numbers. You just need to know how many lines are here, right? Later I'll give you an example of how what they expect you to draw if they don't draw this diagram for you. Right, so this is 4 energy states shown, n equal 1, 2, 3, 4. You can see the gap between 1 and 2 is bigger than the gap between 2 and 3, right? Gap between 1 and 2 is 10.2 EV, right? And gap between 2 and 3 is 1.89 EV, right? So, yeah, and so on and so forth. This is a recurring feature in the energy of electron, right? And how the electron falls determines what type of frequency of photon is produced. So for example, if let's say my electron get excited from ground state to n equal 4, how many ways can I have to come down to n equal 1? Because remember, I cannot stay in the excited state, right? So for me to come down from 4, right, I can come down from 4 to 3, 4 to 2, and 4 to 1, right? So this one already 3 different photons, right? I can equate this remember is a unit for energy. I can equate these to HF and find the frequency of this one, and this one, right? Then if I fall down to n equal 3, I'm still excited, which means I'm still unstable. So I can fall down to n equal 2 and also n equal 1. So if I fall 4 to 3, 3 to 2, and 2 to 1, I produce 3 different photons corresponding to these 3 different energies, right? And likewise, so on and so forth. If I fall off from 4 to 3, I can fall directly from 3 to 1 as well. And this one will be a different photon with different frequency, right? So you can see if I fall from 4 to 1, there are 6 different frequencies of photons I can produce. You see, because it corresponds to these 6 arrows downwards. And this may be something you need to be able to draw yourself in exam. Right, so this uniqueness allows for identification of elements because each element got a different number here. All these numbers are different, right? Therefore, they'll produce a different sort of fingerprint for me to identify the element. Okay, so yeah, so you can see the users here. I'm not going to talk about them. All right, yeah, okay, can that's fine. All right, so we look closely at the hydrogen. All right, so normally we can draw from 4 downwards to 4 to 3, 4 to 2, 4 to 1 like that, right? But more commonly, we draw like that. We draw any level here to 1, any level here to 2, any level here to 3. Primarily because this is the biggest space. That means 1 to 2 is the biggest space. Therefore, this is actually the one that determines the frequency the most. Because this is such a large drop in energy, right? If anything from here drop to 1, it's likely to fall within a spectrum. That means to say, if you look at it carefully, this Balmer series here, everything that falls to n equal 2 is actually visible light. Because visible light lies within a frequency spectrum, right? So because this is such a large gap, right? This determines the fact that I fall roughly in the visible spectrum. And if you look carefully here, this one is higher frequency than visible spectrum. What's the next spectrum that is of larger frequency than visible spectrum? You should know is ultraviolet. So all these are ultraviolet. All this is visible. And you can guess this will be infrared, right? And so on and so forth. I never really checked these two, but my best guess is this is the next neighbor lah. Okay, but I didn't really guess. This could be infrared as well. I'm not very sure. Okay, but this one is visible. This is ultraviolet. This is infrared. I'm not sure about these two actually. This could be infrared. Okay, you don't need to know these things lah, but I'm just telling you generally speaking, this is one way you can analyze the line spectra. Okay, you can only take n equal 1, 2, 3. All right, it must be integer. Ground state's lowest energy level, we talk about this, n approaches infinity. That means I'm no longer bound to atom ionization. So if I look at this atom, you must remember that these are negative because I set infinity, n equal infinity to be 0. That means for me to hit n equal infinity, I need 13.6 eV. So electron here must receive 13.6 eV to hit n equal infinity, which means I'm no longer bounded to the atom. Alright, and therefore that's called ionization. Right, energy levels becomes less negative as n increases. Okay, lower, more negative values, energy states correspond to greater stability. Right, I think this one you can read yourself. And so I talked about it. Yes, I talked about it. Electrons can transition between energy states by absorbing and emitting energy, not only as photons, but through other processes like collisions, right? So of course, I can absorb a photon to go from ground state to the up state, but that one is quite difficult because you must remember electron-photon interaction is 1-1 as per Einstein's theory. That means to say I must absorb the exact the exact photon that has energy level equal to from here to here, right? So it's quite hard to use photon to excite to the correct energy level. More often they use collisions, which means I collide with other subatomic particles. Okay, excited state, and we talked about this. So yeah, see this, the energy of each level is given by En equal minus 13.6 eV over n squared. Right? Can you see this En value is different from the one we learned earlier theoretically from the 13.6? Yeah, it's different from this. So don't confuse the two. That's what I'm trying to say. Do you have to memorize this thing? Answer is no need. Okay? You don't have to know the names of the series also. Lyman, Balmer, Bastian. No need to know. All right? Uh, yeah, okay, down on it. Right, so there are two ways to excite atoms. One is photon absorption, as I said earlier. So the HF of the photon has to be equal to final minus initial. That means if I'm going from, let's say, 1 to 2, then I need to take this value, which is final, minus initial, to know the amount of energy my photon need. Then I equate that to HF, and that's the frequency of the photon that must exist to excite my gas from n equal, electron from n equal 1 to n equal 2. Right, so it's very hard to do. Okay, but you can collide with ions, atoms, or electrons instead. This is easier because as long as the colliding particle got enough energy, right, to excite the electron to the next energy level, the electron will absorb whatever he need and then uh, leave the excess back to the colliding particle. All right, so that means it gives you more room for maneuvering. Later we'll look at example to explain this. Right, the excitation, direct transition and cascading transition. This one we uh, talked about already. Direct is your one shot come down then from 4 to 1. That's direct. Cascading is 4 to 3, 3 to 2, 2 to 1. Right, that's cascading. Yeah, I won't talk about too much about this. Metastable state, I think, is no longer very important. Last time we used to study a chapter that relates to metastable state, but I think currently not really important in your syllabus. Right. Can you pause for a while and try 13? Right, we're back from the pause. Calculate a wavelength to bring an electron from hydrogen atom from ground state to n equal 4. So this is given to you, right? So from ground state here to n equal 4, the energy difference is 12.8 eV. Right, so what's the wavelength? I'll equate 12.8 eV to why is this 0.75? Sorry. I don't think there's any issue. Oh, yeah, it's correct. So 12.75 eV, right? So you just take final minus 0.85 minus 13.6. So it's 12.75 eV, right? So this is the energy difference between here and here. I think this is a rounded value. Okay, this 12.8, but if you go minus, it's 12.75. And this must be equal to the hc over lambda, which means lambda is this value over here, right? Pause a while to do question 14. You may still refer to this one, this diagram. Okay, we're back from the pause, right? The electron again, realize can give partial energy as discussed earlier. So 12.5 eV, right, can help the uh, electron in the hydrogen atom hit which level. So you can see 12.5, can I go from ground to 4? Cannot, because I'm less than 12.8, right? So I cannot go from 1 to 4. So max I can go is from 1 to 3. 1 to 3 requires 12.1 eV. Okay, or you can go and minus the right? So E3 minus E1, I can only jump to E3. So E3 minus E1, right? You'll get some value, and then the leftover energy is whatever energy the electron has left after passing to the unexcited electron. So it passed this amount of energy to the unexcited electron, and this is what you have left, right? State how many transitions are there when hydrogen is n equal 4 state. It de-excites to the ground state. Okay, I'll pause a while and try. Right, we're back. Technically, this one you may not have to actually, they may not actually give you the diagram. That's what I'm trying to say. Alright, so let me see if I can get my pen out. Right, so what I'll do is I'll just try and draw out the states n equal 4, n equal 3, n equal 2, n equal 1. Right, then I'll try to think about what are the possible transitions. Remember that this gap is the biggest, but in this case not so important. So n equal 4 can fall down like that, then it can fall down like that, then it can fall down like that. Right, then it can also fall down to this directly. Then this one is the same. Right, so I don't have to care about this one already. Because it's the same as the first one. Right, then it can fall down all the way. Right, and of course, you think about it, there's one more whereby if I fall this way, right, I can fall this way. Right, so there's 1, 2, 3, 4, 5, 6. Okay, think about the general combinations that can happen. Right, you can think this way, or you can just, if your mathematics is good, 4 choose 2, answer is 6. Right, so this kind of thing you can decide how you want to do it. Generally, I'll just draw it out by logic, but depends on you how you want to do it. Right, with that, yeah, stay tuned for the last part of the lecture coming up, which is line spectra. Yeah.